Association of Switzerland's tonight's talk on the cosmological perspectives of Bitcoin. Among all the topics we had so far, maybe the most comprehensive we ever had. So the idea to this talk was born at our annual Lakeside party last year, when Ellen was talking about the relevance of black holes and the importance of hashes. So I really couldn't follow his logic, but I proposed to have a talk on it. But then he doubted that it was worthwhile doing it. So I proposed him a deal. You do the talk, I do the t-shirt. So here we are tonight. There is a lot of doubts along a lifetime. And for instance, when you're organizing an event like this, you have 20 registrations, but only 3 tickets sold. And then at a liquor store, you have to make a decision, do I buy now 3 beers or more? And it's worse when you know that Ellen is going to talk 1.5 hours, and you know people will be thirsty, so you better buy more drinks. So there is enough drinks tonight.
I'm here.
And once in a while, it's maybe a good thing to remember what a guy a long time ago wrote about doubts. He said, you can doubt everything but the fact that the process of thinking exists. And for this process to work, there is something needed that executes it. And that something is our being. In other words, I think, therefore I am, or in René Descartes' words, cognito ergo sum. And in this spirit of doubtlessness, I'm passing the word to Alan and his presentation. Thank you for being here.
Thank you for that marvelous introduction. I'm touched to be the cause for having enough beers. That's good to know. Good to know. The way this presentation came about is exactly as Stefan described it, or at least his memory of events coincides with my memory of events. Who knows? It was the Bitcoin Lakeside party after all. Bitcoin and black holes. Your first reaction, well, you should have 2 first reactions. The first reaction should be, what on earth does Bitcoin have to do with black holes? And secondly, why am I choosing to depict black holes with a picture of a baby? Well, the second answer is actually really, really straightforward. Babies resemble black holes in more ways than one. They suck and swallow time. And if you were wondering why it took me so long to deliver this presentation, the reason is obviously that I spent a lot of time in close proximity to a baby for research purposes, of course. And so the other question, what does Bitcoin have to do with black holes? That's the one that I'm going to try to answer in this presentation. Okay. And this is a table of contents, except I'm afraid I'm not going to go through this rather linearly as the table shows. It's more of a graph of contents, and so I've divided this talk into approximately the right way to divide this graph into subgraphs. And so part 1 will talk about cryptography and computational complexity and Bitcoin's position in that whole subfield of science. And then I'm dividing physics into relativity on the one hand, that's part 2, and information theory on the other hand, that's part 3. And then the point where all these 3 branches come together, that's in the black hole information paradox. And so yes, there definitely is a link from Bitcoin to black holes, and you just have to travel. You don't even have to travel all the way across the slide. it's pretty close, but you are traveling from one branch of science all the way into another branch of science. But it's okay, it's okay. So yeah, in the last part of the presentation, I'll be talking about the black hole information paradox. Disclaimers. I am a cryptographer. I do crypto. I don't do physics. What I'm saying about physics is probably wrong. Feel free to correct me. But the point is, when physicists, people who do physics as a profession, when they talk about physics, they're also wrong. The whole point is to become more informed about the universe, to disillusion yourself to a slightly larger extent. But whatever model we have in our heads of how the universe works, it's an approximation anyway. So yes, I do crypto. Take what I say with a grain of salt, but take what physicists say with a grain of salt also. This resolution of the black hole information paradox is controversial. So even not all physicists agree. They're full of shit, of course. I'll get to that, but it's not. There's no consensus mechanism that forces them to agree. And there is a paper. I mean, there are several papers, but the one that I was hoping to find, the one that links black holes with hashes in particular, I actually couldn't find it. But that's okay, because if I could find it, I wouldn't be able to read it anyway, because it's kind of over my head. And I did find lecture notes. And so these lecture notes by Scott Aronson and I guess two others whose names I don't know are very worthwhile. They were my source for preparing this presentation, and they are very worthwhile reading if you can't sleep for whatever reason. By the way, Scott Aronson is a wonderful writer. He's a quantum computers researcher, and he manages to write in a way that even little old me can understand. And so you can do a lot worse than reading Scott Aronson if you want to learn about quantum information theory and quantum computers. All right, so much for the disclaimers. Why is there such a big delay on the clicker? Okay, part one. Bitcoin, computational complexity, cryptography, they're all related. And, well, obviously, crypto is cryptography. I used to have a slide where I went through every individual point on that graph, and so there was an animation showing that crypto is cryptography, but I decided to cut that for the sake of time, and instead take more time explaining, because I'm not very efficient. All right, so suppose I gave you the task of designing Bitcoin or designing a cryptocurrency. What kind of fields of computer science or fields of knowledge would you need to study up on? What are the notions that you need to combine into a protocol? And as it's also worthwhile noting that Bitcoin isn't really unique in this sense. This argument applies to any cryptocurrency. Bitcoin does have the biggest economic security argument. The fact that crypto is possible, Bitcoin is a better argument showing that cryptography is possible than any other cryptocurrency is, because Bitcoin is the bigger bounty to anyone who breaks cryptography. Okay, so you need some kind of networking, you need some kind of distributed databases, you need some kind of consensus mechanism, you need some kind of mechanism to guarantee that you can own these digital assets and transfer them to the next owner. You need also some notion of time, and I'd say this list is probably not exhaustive, but you have to think long and hard before you can find something that belongs on this list. And on this list already there are two ingredients that fall in my field, which is the consensus mechanism and the mechanism for ensuring ownership and transfer. And concretely, the consensus mechanism involves hashing, and ownership involves digital signatures. And these are two applications of cryptography. Crypto means cryptography, obviously. And so it's absolutely no shortcut at all to say that Bitcoin requires crypto, and it's also present in the name cryptocurrency to describe not just Bitcoin but also other currencies. Crypto is an essential ingredient. Okay. Cryptography, or crypto, I would define as the science of protecting information. Based on that definition, you can classify, or partition rather, cryptography into various subfields depending on how that information is being protected. Sometimes you manage to protect information theoretically, and those types of cryptography are really, they give you a high level of insurance, but they're typically very difficult to use, but they do exist. Then we have complexity theoretic cryptography, where we use mathematical hard problems to protect information. That's cryptography as we usually use the term, but you can come up with other forms of cryptography. For instance, non-computational cryptography, like locks and keys, still exists. You're hiding information in your flat when you lock your flat. You're hiding information inside of an envelope, and you're protecting that information from weather or from wear or from prying eyes. With a seal on that envelope, you are ensuring authenticity of the information contained. And also money and cash, I would say, is a carrier of information, and therefore money itself has to be qualified as a form of cryptography. That may be a little bit of an occupational hazard that causes me to see all of the world in the eyes, through the lens of cryptography, but I think the argument is valid. And lastly, you might also consider using quantum as a protection mechanism to protect information. And sometimes that makes sense, and sometimes this doesn't make sense. And so I think quantum money is a fantastic application, and it would be really, really nice if we all had quantum computers. But until that time, I'm afraid it's only a cool idea. And QKD, quantum key distribution, which is presented as a quantum solution that doesn't require quantum computers, that's complete shit. But unfortunately, most of the time, when people say quantum solutions, they mean this, and it really doesn't have any applications. So yeah, take what physicists say with a grain of salt. This talk focuses mostly on the complexity theoretic part, or at least complexity theory is central to this talk, and especially hash functions. Why hash functions? Okay, so that question I'll answer later on. In terms of cryptography, complexity theory, I also need to define. It's the branch of computer science that deals with the study and classification of computational tasks based on the algorithms that solve them and the resources that those algorithms require. And so, if you were to ask me to place databases, number theory, numerical mathematics in a Venn diagram, most of these fields fit either squarely in computer science or else squarely in mathematics, but there are three things that I think fall neatly in the intersection and that's numerical mathematics, computer algebra, and complexity theory. Because we get the problems from mathematics, but we try to solve the problems using algorithms, and then we analyze how complex are those algorithms. So it really is in the intersection between computer science and mathematics. Okay. Where do the problems come from? They can come from various sources, but most of the time, strictly mathematical sources. So we can have graphs, we can have lattices or coding theory. The third one is a depiction of a Turing machine, and so yes, there are purely computer scientific origins of hard problems. And the last one is the most mathematical origin of hard problems. It reflects number theory. Number theory is a rich source of hard problems, and the one here is actually the factorization problem. If P and Q are two large primes, then it's difficult to find P and Q from their product. And that fact is actually used in the RSA crypto system. Okay, good. Next up. Complexity theory classifies problems based on the resources that the best algorithms for solving them require. And so if all your solving algorithm requires is time, and it's a fast solving algorithm, we might say that your problem belongs to P. Formally, that's the class of problems that can be decided in polynomial time as a function of the size of the input. But you can extend P with other resources like non-determinism. What if your algorithm can make a guess and be guaranteed that whenever he makes a guess, he is guessing correctly? What problems can you solve efficiently in this model of computation? And that is exactly the NP class. And then another class of problems is bounded, bounded probability quantum polynomial time. And that's where you don't get to guess correctly every time, but you do get to have access to a quantum computer. And you have to be an efficient algorithm. And so, based on the resources, you can classify hard problems. And the fact is that most of these classes, we have absolutely no clue how they relate to each other. And so one of the biggest open, outstanding mathematical conjectures is P versus NP. That's the class of problems that are efficiently solvable. Is that class the same as the class of problems that are efficiently solvable if you can guess correctly every time? And another way of phrasing the second class is the class of problems that have efficiently verifiable solutions. We don't know, and it feels as though the answer should be obviously different. That the answer should be obviously that these classes are different, but we don't have a proof to that effect yet. So as far as complexity theory goes, there are lots and lots and lots of questions. And based on those questions, cryptography works or doesn't work, or works only to some extent. Let me explain. In the worst possible case, most pessimistic case, we live in the world called algorithmica. P equals NP, and so any problem that you can articulate that still involves a secret key can be solved by an attacker who doesn't need to have the secret key, because the attacker can guess the secret key and he's guaranteed that the guess is correct. So if we live in this world, all cryptography is hopeless. If we live in heuristica, there might still be a proof that P is different from NP, but in practice, once you start attacking cryptography, you're always going to be successful. So if we live in heuristica, cryptography is also going to be hopeless. And then the last pessimistic world we could be living in is Pessiland, which means P is different from NP, and in practice there are hard problems, but we cannot build crypto systems out of hard problems. And it's also a plausible scenario. So the symbols on the right mean there does not exist one-way functions. And that's important to remember because that is the key complexity theoretic proposition that I will be marrying with black holes. Next up we have mini-crypt, and that assumes the existence of one-way functions. Thereby it implies that P is different from NP. But since one-way functions exist, we can do cryptography. Okay, next up we can do something more than just symmetric key cryptography. We can do public key encryption, which is not implied by the existence of one-way functions, but it's cool. So basically, the fact that we have encrypted internet implies that we live in cryptomania. And then there's one more level, that's where you have indistinguishability obfuscation, and that's essentially a cryptographically obfuscated code that you can outsource to AWS or Microsoft Azure, and they won't be able to extract anything from your code. There are suggestions, proposals for achieving indistinguishability obfuscation, but they're really not practical. So I drew the "you are here" arrow one level down. We believe we have public key encryption, but actually this is an assumption, a complexity theoretical assumption, and we don't know how to break it, but there's definitely no proof that breaking it has to be hard. We believe we are in cryptomania, but all we need for Bitcoin to work is mini-crypt. We can build the cryptographic primitives on which Bitcoin is based out of just one-way functions, if you think the cryptographic primitives are hash functions and digital signatures, right? Hash functions we need for the consensus mechanism, digital signatures we need for ownership. Now, Bitcoin technically uses a slightly more sophisticated one-way function than just any one-way function. It uses the elliptic curve multiplication, and so you get efficient signatures. But with just hash functions, you can already achieve rudimentary signatures, and that's enough for Bitcoin to work. That was part one. Time to take a breath. Up next, general relativity. Okay, so I'm going to present a historical picture of how general relativity evolved that is ahistorical, because I want to keep relating it to black holes. And so I'm going to start with the idea that black holes might exist and show how that idea could have evolved simultaneously with general relativity, even though general relativity had to exist before Schwarzschild came up with the notion. And so the idea is you're standing on a planet of mass m and you throw a tennis ball into the air. Where does it land? And in order to answer that question, you need to know the angle and how fast you throw it, and maybe also the radius of the planet you're on. And for simplicity, let's assume that the angle is straight, so you're throwing it exactly opposite to the center of the mass of the planet you're on. And then there's such a thing as the escape velocity. So there is an escape velocity. That means if you throw the ball slower than the escape velocity, it will fall back to the planet. And if you throw it faster than the escape velocity, it'll continue going forever. And so I was tasked with finding the radius of a black hole, assuming the speed of light was constant. I was tasked to do this, by the way, in high school, where I was not exposed to general relativity. This is just Newtonian mechanics, but assuming a constant speed of light. And so the question is, what happens if your tennis ball, what happens if your light particle travels at a speed that is slower than the escape velocity. Well, your light will just fall back and it will fail to escape from your planet. Okay, that's fine. You just build a bigger rocket. You have to travel faster than the speed of light to escape from the planet. Okay, big deal. Okay, maybe it is a big deal, but in order to understand why that would be a big deal, we have to continue along the line of relativity. So the speed of light was first established to be finite back in 1676 by a guy called Romer. I don't know how to pronounce these Danish names. And then this was given some theoretical support by Maxwell in his equations of electromagnetism. He, by the way, showed that light is an electromagnetic wave, and like all waves do, it travels with a certain speed relative to its medium. And then they called the medium ether. And they tried to measure the speed at which Earth travels through the ether, which is a nice thing to do. And while they tried to make that measurement, they saw that Earth travels at the same speed through ether wherever you measure it. And that doesn't make any sense, right? Because if the planet Earth is moving through ether, then you should measure a different value in winter than in summer. Or you should measure a different value in the morning than in the evening. And they made zero difference. That was their observation. And so that basically killed the notion that that light has a medium. And so either Maxwell's equations had to be wrong, because light cannot be a wave, or at least it cannot propagate as Maxwell thinks it does, or Newtonian mechanics has to be wrong, because Newtonian mechanics assumes that you can always take a different frame of reference. A moving frame of reference is no problem, according to Newton. And Einstein, in 1905, this guy said, well, what if there is no contradiction, right? What if we can have simultaneously moving frames of reference and the correctness of Maxwell's equations? And so his thought experiment can be articulated as a moving train containing two clocks. One clock is based on, I don't know, sand and gravity, or a spring somehow, some mechanism that doesn't work based on light. And the other clock bounces a particle of light between two parallel mirrors. And by counting the number of bounces, you can determine what the time is. And the key of the thought experiment is that relative to an observer, the train is going slow or fast. And that means that the distance traveled by the particle in between ticks is larger or shorter. And so, if the observer looks at the train, he has a watch, the light must be traveling at that speed. Hang on. The person in the train must be measuring the same speed of light, even though the light is traveling bigger or smaller distances in the same time span. And the argument is that if you could use the second clock to tell in which of these two worlds you live, then you would break the assumption of relativity, which is that the speed of light is constant in every reference frame. And therefore the second clock cannot exist. So the conclusion of this thought experiment is that the speed of light is the speed of causality. And that's kind of a problem when it comes to black holes, because that means that you really can't build a bigger rocket. because nothing can escape from a black hole. All right. We have special relativity that deals with the speed of light, speed of causality. Fair enough. But, well, maybe you don't have to build a rocket that goes really fast. Maybe all you need is just a rocket that keeps on accelerating. And so the question of acceleration and gravity was still open, right? Because in the eyes of the same Einstein, the world in which you are in a rocket undergoing a constant acceleration and the world in which you're standing on a planet undergoing a constant attraction due to gravity, those are not the worlds that his special relativity spoke of, because he was assuming no acceleration at all. So these two worlds, special relativity cannot say anything about. And Einstein postulated, well, if it can't say anything about the world on the left, and if it can't say anything about the world on the right, maybe they're not so different. And so Einstein's second postulate was to say, what if there is no difference? Meaning, what if there is no experiment that we can perform that could tell you whether you are experiencing this sensation of acceleration due to gravity or due to being in a rocket? And based on that assumption, Einstein developed general relativity, which is a complete description of gravity that we still use today. That completes the first part of the timeline of general relativity. The rest is really deriving from Einstein's equations. So 1 year later, Schwarzschild came up with a solution to Einstein's equations involving, you guessed it, a black hole. And then Bekenstein married black hole with thermodynamics. And Hawking married the existence of black holes not with, he married it with quantum physics, but only from a special relativity point of view, not from a general relativity point of view. And in 2016, researchers at LIGO, the Laser Interferometry Gravitational Wave Observer, they dropped the W from the acronym. They actually measured waves, gravitational waves that could only have come from black holes. And we even have images of black holes. And so this is our home black hole. This is Sagittarius A star, which I think was imaged in 2017. This is the supermassive black hole at the center of the Milky Way. So we are orbiting this guy. And of course, you're not seeing the black hole, you're seeing the accretion disk around the black hole. You wouldn't be able to see a black hole because it's black, obviously. Nothing escapes from a black hole, or at least in the conception of black holes right up until 1972, nothing escapes from a black hole. Okay, so what do you need to know about black holes? Firstly, black holes form spontaneously whenever you have matter that is too dense. Hang on, that animation could have gone better. Whenever you have matter that becomes denser and denser and denser, at some point, poof, it turns into a black hole. A black hole consists of the singularity at the center, which is a point of infinite density, and the event horizon at the edge. As you get closer to a black hole, time starts slowing down, and so the event horizon is called the event horizon because that's the point where time stands still. That's for observers standing sufficiently far from the black hole. If you were to travel there, you would experience time as usual, and if you were to travel across the event horizon, you would go straight to the singularity. Okay, next up. Black holes emit Hawking radiation. And as a result of emitting Hawking radiation, they lose mass. And at some point, poof, they disappear. Because there's a conservation of mass equals energy. And so if they lose mass, there must be less mass left, or less energy left, however you measure it, and so at some point they must disappear. But that process takes ages, as in 10 to the 60, 10 to the 100 years, very, 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 very long. The black holes that were present at the formation of the universe, if there were any, they're still around. So all of this evaporation is assuming that Hawking radiation, that Hawking was correct. It's not actually an observation. Okay, next up, we have part 3. Time for another break. Thermodynamics. You may have heard that thermodynamics, entropy, and chaos are 3 almost basically the same thing. Certainly, when I was taught thermodynamics in the first year of engineering school, there was no mention of chaos or degree of disorder. We were taught thermodynamics from the point of view of analyzing whether engines can exist, and if they do exist, how efficient they are. And so we were shown the Carnot cycle of a heat engine. A heat engine works by trapping a piece of gas, then exposing that gas to a hot heat reservoir in stage between 1 and 2, where so the pressure reduces, the volume increases, but it stays on the same temperature as the hot heat reservoir, and thereby it absorbs energy. And then in the next stage, the pressure decreases more, the volume increases more, but this stage happens in isolation from other heat sources. And then in the next stage, we start compressing, and so the volume decreases, the pressure increases, but at this point, the gas is exposed to a heat source of low temperature, thereby sending energy to the heat source of low temperature, the cold heat reservoir. And then in the last stage, we compress even more, but isolating the gas from both heat reservoirs, and that makes makes it all into a full circle. And this is the Carnot engine. This was the first postulated theoretical analysis of engines, how they could work. These are all heat engines, by the way. This was way before combustion engines could work. And so the key thing is that you need some kind of temperature differential in order for engines to work, right? You need to have a hot source of energy and a cold source of energy, a hot temperature reservoir and a cold temperature reservoir, and those temperatures have to be distinct because otherwise you cannot extract energy. Even if the temperature is higher, if the difference is lower, you won't be able to extract as much energy. And so relative to this picture, we were told the entropy is just the heat energy divided by the temperature. It's a very, very crude simplification, but it allows you to start doing calculation. And so the second thing we were taught, and one is actually accurate, this is the second law of thermodynamics, and it says that the entropy has to increase or stay the same over time for any closed system. And so concretely, the system depicted here is actually an open system because there is a hot heat reservoir and there's a cold heat reservoir. But if you include the heat reservoirs, then the second law of thermodynamics predicts that the temperature in those heat reservoirs has to change. The temperature differential has to degrade over time. And so if you let this engine run long enough, eventually everything will be the same temperature, according to the second law of thermodynamics. And okay, that's really nice. But then comes Bekenstein, Jacob Bekenstein in 1972, and he says, okay, what if we use a black hole as a cold heat reservoir? And that's a problem because that kind of breaks thermodynamics. Because heat is not something you're supposed to be able to get rid of. If black holes exist, then it's possible to guarantee that there is a non-zero heat differential forever. And so you would be able to reduce entropy of the universe just by sending your heat into the black hole. And so that's a problem. And so what's the solution? Black holes have a temperature, non-zero temperature. Black holes have a non-zero temperature is the resolution of black holes with classical thermodynamics. Well, actually, it's even worse, right? Because if I can use it as a cold sink and they have a temperature, then I can also use it as a hot heat reservoir. And so black holes have to adapt, like all heat sources, like all heat reservoirs do, to engines that operate on them. And so Bekenstein, before Hawking, already predicted that black holes emit heat, except heat is obviously a form of radiation. Hawking gave a quantum mechanic explanation of where that radiation is coming from. But Bekenstein came to that conclusion before on thermodynamic considerations.
Question?
Yes?
Is this a theory, or is there actual empirical evidence that this is the case?
There is a lot of empirical evidence that the second law of thermodynamics holds. There is not too much empirical evidence that black holes behave the way we expect them to. Because the nearest black hole is Sagittarius A star, and you have to travel halfway a full radius of the Milky Way to get there. So most of what I'm saying in this talk is just thought experiment building on top of thought experiment. Very little practical observations here. And so when I say observation, it's really only observation in your mind. Okay, so that was classical thermodynamics. Let's look at the slightly more modern, but by comparison still rather old branch of statistical mechanics. So in statistical mechanics, what we attempt to do is we attempt to assume that all the particles in a system behave more or less randomly, and then we want to analyze which properties emerge, which macro scale properties emerge from these random interactions at the micro scale. And so your macro properties might be pressure, volume, and temperature, whereas your micro state, the description of the system at the micro level, might be the velocity and momentum of the position and velocity of every particle in the system. And relative to this disambiguation between macrostate and microstate, you can define entropy as the logarithm of the number of microstates that is consistent with the observed macrostate, or with the considered macrostate. And so for a concrete example, I have here two systems containing two chambers and 24 particles. In the top example, the particles are spread 50-50 across both chambers, and if every particle has to be in one chamber, there are 24 choose 12 microstates that are consistent with the macrostate that says they're spread 50-50. 24 choose 12 is a big number, and so taking the logarithm of 24 choose 12 is still a big number. And so the entropy of the top world is very high. Conversely, in the bottom world, all the blue particles are on the left, and all the red particles are on the left, and all the blue particles are on the right. And there is only one distribution of particles, there's only one distribution of particles that is consistent with that high-level description, and therefore the logarithm of 1 is 0, and therefore the entropy of the bottom picture is 0. And in fact, you can apply the same reasoning whenever you have a distinction between a macrostate and a microstate, but if you were to apply it only to particles, their position and their velocities, then you get emergent laws of thermodynamics that just coincidentally agree exactly with the classical laws of thermodynamics, including the preservation of energy, and including the second law, which states that entropy always increases or stays the same. The caveat is that these laws emerge only with very, very high probability, and so if you pray hard enough, then the entropy can go down, but short of hard enough prayers, it cannot go down. Okay, very good.
You go down for a very short time, right?
I guess.
Yeah.
I guess the real counter argument would be if your prayers can make the particles behave in the way you want them to, then your microstates should take into account what you are and what you are not praying for. And once you start taking that into account, it's the same story all over again. You cannot decrease the entropy of the universe. Okay. This didn't sit well with Maxwell. And he postulated that the second law of thermodynamics has to be wrong, or at least there has to be something wrong with it. Maybe it's not wrong in its entirety, but there's a problem with it, because I can postulate that there is this system consisting of two chambers separated by a door in which a demon lives, who opens the door and closes it just to ensure that all the blue particles go to the right and all the red particles go to the left. Every time a particle comes closer to the door, he either keeps it shut, if it has to stay in the same chamber, or he opens it to let the particle pass through. As you let the system evolve, it will tend to the state where all the blue particles are on the right and all the red particles are on the left. And it doesn't require any energy to open that door. So what's wrong? This is a closed system, and the entropy is decreasing. Well, what's wrong is this demon has to know when to open the door and when to keep it closed. And in order to know when to open the door and when to keep it closed, he has to store information about those particles, and he has to operate on that information about the particles in order to know to keep the door open or to keep it shut, or to shut it.
Yay! Break. Why does the demon does not take energy to open or close the door?
In principle, the door can be made of zero mass, or infinitesimal mass.
But you drew the database outside of the system, so there is a leak in the argumentation line. Right?
Because of the picture.
Du bist auf dem falschen Fernsehen.
Nee, wegen dem. Was?
Nein.
Ja, ich
so.
weiß, ich suche.
Wouldn't the demon, by observing the particle, change the way the particle behaves?
This thought experiment came from Maxwell already, and that was way before quantum mechanics existed. So in Maxwell's world, there was no such thing as the observer changing the observed. But the resolution did come only after quantum physics was established as a field. And the resolution is that this database or this computer based on which Maxwell's daemon keeps track of the information of all these particles, there are two ways to implement this computer. You can use a reversible computer or you can use an irreversible computer. If you use a reversible computer and you do the experiment, then you have to take into account the state of memory before and after he separates the particles into two boxes. And so he starts with an all zero memory. He separates the particles left from blue, and then his memory has to be all scrambled up, reflecting the original state because it is a reversible system. Alternatively, you implement it irreversibly, and so you forget information, but in order to forget information, you have to set bits and set them regardless of their value before you applied that operation, and that requires energy. So if you're going to implement this irreversibly, then you're going to radiate energy into space. And so in a closed system, the entropy is staying the same. In a non-closed system, the entropy is allowed to decrease. So there is no contradiction, but you have to consider reversible versus irreversible computations.
Next.
Speaking of irreversible computations, actually, I think Martin's suggestion is a pretty good suggestion. Let's try and ignore as much of quantum mechanics as we can. Let me just stress the points that are really, really important, which is, firstly, quantum mechanics operates on an exponentially large state, and secondly, the operation that is applied on this exponentially large state is that of a unitary matrix. I'll explain these two key phrases in just a second, but all the rest of quantum mechanics we can forget about. So here's on another way, it's another thing. I'm going to describe, using pseudocode, a function that you might even consider implementing on your computer. And the reason why I'm going to describe this is because this computer program also has an exponentially large state. I'll explain. So let's define a function h of a that starts with a bit string b, and then you define a probability distribution over bit strings. So C is the probability distribution, meaning that it holds 2 bits, but which 2 bits depends on how the dice land. Okay, and then you can do bit operations on these variables. So you can XOR B with C, no problem. Or you can XOR C with itself, no problem. You can do all sorts of bit operations. You can concatenate them. You can define uint32 addition on these probability distributions over bit strings. Exponential means there are exponentially many probability values as a function of the number of bits in your bit stream. That's what I mean by exponential. Another observation here is also that whenever we have a probability distribution, sooner or later we are interested in sampling it. So let's add the restriction to this program that whatever comes in between, in the end we get a probability distribution, then we sample it, and then we return the sampled value. That's nice, okay. We know what exponentially large is. And we actually also know what stochastic means. Stochastic is not yet quantum, not even close. Stochastic means that whenever you have one of these variables that represents a probability distribution, the sum of all probabilities is 1. This is obvious, right? But stochastic actually means it's any transformation that keeps that property true. You go from one probability distribution to another probability distribution, but before and after you are guaranteed that the sum of all probabilities equals 1. And so if you're a little bit like me, and curious and a little bit nerdy perhaps, you might start wondering, okay, this is one interesting invariant defined on vectors. What other invariants can we define, and which computational problems could they define, and which computational models do they define, and which problems fit in those computational models? And you would quickly come to the conclusion that there is another viable option for an invariant that is preserved before and after transformations, and that is that you have to square every number before taking the sum, and that sum has to be 1. You have to square the absolute value, right? So this is no longer dealing with probability density functions, or no longer with probability distributions, but it's still some kind of distribution of, let's say, amplitude, to use a generic word. And we're requiring that if you take the absolute value, square it, and sum it, then it has to be 1. And then we can define unitary as the property that whenever you apply operations that make sense on bit strings for which this invariant holds, the invariant still holds. Okay. If you're with me so far, congratulations, you're a quantum computing expert. So the difference between classical computers and quantum computers really is that second invariant where you have to square before summing. All the rest, I promise you, is bookkeeping. And so we can divide the two modes of computation in the stochastic mode and the unitary mode, which correspond nicely with the classical information, quantum information, or classical computation, quantum computation. And key things to remember here is that classical computations are not necessarily reversible, whereas quantum computations are always reversible. That's because they are unitary. Unitary matrices are invertible. Stochastic matrices, not necessarily. That also means that it is easy to erase classical information, but it is not easy, or it's impossible to erase quantum information. And lastly, it is easy to clone classical information, and that's what makes Bitcoin such a tremendous breakthrough, because all of a sudden there is information that you can't copy from one computer to another. In the quantum case, it's actually true by default. You cannot copy quantum information, and that's why quantum money is possible. You cannot, it's money that you cannot copy if the laws of quantum physics are correct. Quantum money is really cool. Quantum key distribution, lest you forget, is absolute shit. And I'll tell you why it's shit. It's not even sophisticated shit. I'll tell you exactly why. The theory is that we're using quantum mechanics for Alice and Bob to establish a shared key using quantum information, and since it's quantum information, it is subject to the no cloning theorem, and therefore there can be no eavesdroppers. Amazing theory. How do we attack this? Well, there's no authentication, is there? So if you're going to deploy a quantum key distribution scheme, I'm going to insert myself in the middle and establish a secure quantum key with Alice and a secure quantum key with Bob. That's different. And so the only way to get around this man-in-the-middle problem is to assume that Alice and Bob have a shared key already that they use to authenticate each other with. But that undermines the whole point of distributing a key in the first place. Why would you use quantum mechanics to distribute a key if the keys are already present? Well, the hardcore QKD's fans, they would say that it allows you to extend the length of a key without relying on mathematical assumptions. We rely instead on quantum mechanics. And even that is bogus, right? Let the physicists break AES first, and then we take them seriously. Sorry for that rant. Okay. On to part 4. This is the nice part. Well, the other parts were nice too, but this one especially. The black hole information paradox. Well, we already saw an information paradox where black holes come into contact with classical thermodynamics, because apparently you should not be able to get rid of heat by sending it into a black hole. Or at least you shouldn't be able to use that to reduce the entropy of the universe. And it's actually a lot more intricate when you involve quantum information theory. Okay, so first paradox. We take a little bit of quantum information and we throw it in the black hole. Quantum mechanics predicts that information cannot be destroyed. General relativity predicts the no-hair theorem, which stipulates that a black hole is completely characterized by its mass, its position, its velocity, and its angular momentum. There is no hair extra to define or distinguish black holes with. Therefore, if information falls in, compared to another black hole, it is perfectly indistinguishable. And that's a problem, because you shouldn't be able to get rid of information. So either the black hole is described using quantum mechanics, or either quantum mechanics is the root theory of the universe, and the black hole behaves quantum mechanically because everything does, and then the information should still be there. Or else general relativity is true, the information does disappear, and we need to revise quantum mechanics. Okay. But Bekenstein already showed that black holes have to emit heat. And Hawking confirmed that by coming up with a quantum mechanical explanation of where that heat is coming from. It has to do with the nature of the event horizon, or with virtual particles at the event horizon. And so the the Hawking-Bekenstein radiation emitted by the black hole provides a potential resolution to this paradox. The information is not destroyed, it is only transformed into heat, or into Hawking radiation. Unfortunately, there are still some paradoxes that remain. So, if the radiation is thermal, as Hawking and Bekenstein predicted, that means that there is no correlation in any observed signal between itself or between other signals. Whereas if the equations that govern black holes really are, or if quantum physics really is the governing rule of the universe, then there must be a unitary matrix, a unitary transformation that describes how quantum information is transformed into thermal radiation, into uncorrelated information. And that's a problem, right? Because there is no unitary matrix that sends a pure quantum state into uncorrelated information. This unitary doesn't exist. It would imply that the unitary matrix is not deterministic, and that doesn't make any sense because the matrices are not capable of being non-deterministic. So this is a problem too. The emitted radiation cannot be purely thermal, or if it is thermal, it cannot be that there's absolutely no correlation. And so one possible resolution to this paradox is that there can be correlation as long as you cannot observe it. Okay, I buy that. Might be difficult to observe correlations, right? Just like it might be difficult to prove that something is random. That's exactly what it boils down to, right? How do you prove that the correlation is not there? You prove that the correlation is not there by proving that it is random. You cannot prove that something is random, as this cartoon by Dilbert shows. Dilbert is introduced to the random number generator who says 9999, and in fact maybe he's just reciting pi from the right digit onwards. Doesn't seem random, but how do you prove that it's not random? Or if it is, how do you prove that it is random? And so I think it is a credible resolution, because no correlation, you need to establish that no correlation exists before that statement is even meaningful. So no observable correlation really means no statistically verifiable correlation. All right, this is what gets me excited, because verifying statistically that a source is random, why, that's a computational process. It's a computational task with a certain complexity. And now, all of a sudden, we're back in the field of computational complexity, because I know a thing or two about computational complexity. Okay, and so the resolution, hang on, before we get to the resolution, here's what we need to know from Don Page, who argued that the entanglement entropy, which is different from the correlation entropy, but it's similar in spirit, the entanglement entropy of the particles emitted through Hawking radiation by a black hole has to decrease at some point. I'm not sure how he got this derivation from black holes, but it does follow from quantum physics. If you start from a pure state, apply some transformation, and then start collecting qubits, at some point you will establish some entanglement. And so if the black hole transformation is itself a unitary transformation governed by the laws of physics, the Hawking radiation has to undergo the same process. At some point you will see entanglements. Okay. So that gives rise to the following paradox. I don't recall the names of the thinkers who came up with this thought experiment, but I can articulate how the experiment goes. So suppose we know the equations that govern the life and death of black holes. Suppose those equations are conformant with the laws of quantum mechanics, and so this is a unitary matrix, pretty big unitary matrix, but that doesn't matter. Suppose we start from a pure state, a state we know, a piece of information, particles that orbit each other, whatever. The point is we know the state, and we make it into a black hole. And so we apply this quantum transformation of black hole evolution to the state. We get a black hole. We observe all the Hawking radiation that is being emitted by the black hole. That's R. And at some point, after the page time, after the halfway point, when we know we have to start observing entangled qubits, we observe the next qubit coming right off the event horizon, that's B, and we bring R, we decode R, descramble R, in order to prove statistically that there is an entanglement between R and the B qubit. And then we jump into the black hole and we measure the matching qubit to B. So the way these qubits are generated at the event horizon is always in pairs. One falls into the black hole, one is emitted as Hawking radiation. And so as they are generated, they have to be entangled. But B also has to be entangled with R after you decode R. And that establishes a contradiction. Because according to quantum mechanics, a single particle can only be entangled with one other particle. And in this thought experiment, the particle B is entangled with the particles R that were observed already, as well as with the particle H. Well, it's not really a contradiction, because in order to observe this contradiction, you have to jump into a black hole. And it's a valid position to take if you want to say physics should only be able to describe the region of the universe where we are capable of receiving signals from. And since we can't receive signals from a black hole, it's okay for the inside of black holes to be beyond what physics can explain. I think that's chickening out. I think the laws of physics should also hold inside black holes, because from the point of view of a local observer, you can travel across it, at least in one direction. I find the complexity theoretic resolution much more compelling, which goes as follows. Same thought experiment, but we want to decode R, demonstrate the entanglement with B, then we jump in and observe H to demonstrate the entanglement with H. In order to do this, you have to solve the decoding problem first. And all right, you know the equations that govern black hole evolution. We don't know them yet, but in this thought example, the experimenter does. Even then, it might still take a lot of time to decode R and establish the entanglement with B. This is potentially a complex task. Certainly, if the unitary is close to random, this task is infeasible. And in particular, it takes time, a lot of time, a lot of time. And so it might be argued that before you can even make a dent in this decoding task, the black hole would long have evaporated. And so the evaporation time could be a lot less than the decoding time. And so in order for this whole thought experiment that supposedly demonstrates a contradiction to work, we need a complexity theoretical assumption, namely that the decoding time is less than the evaporation time. And it's actually quite plausible that the opposite is true. In fact, the opposite gives rise to a very concrete complexity theoretical assumption. And this is what brings us a little bit closer to hash functions. At the start of the talk, I mentioned I didn't read the paper, not this one, but the next one, the next result that I'm about to show, that's the paper I didn't read. That's the one that justifies having hashing on this t-shirt. It's a result by Aronson, who says that If one-way functions exist, then this decoding task is infeasible in the allotted time. That's just mind-blowing, right? If one-way functions exist, then there is no contradiction between relativity and quantum mechanics, at least as far as the black hole information paradox is concerned. That's totally amazing, right? Because remember, one-way functions, okay, on the one hand, they imply that this decoding task is difficult, but on the other hand, they give us hardcore predicates, they give us pseudo-random number generator, they give us hash functions. Hash functions give us one-time signature schemes, and one-time signature schemes can be used to generate digital signature schemes, many-time signature schemes, and boom, then we have Bitcoin. And so, Bitcoin existing and being capable of transferring money from one person to another person is the best indicator yet that we live in mini-crypt. That the right complexity theoretical conjectures are true in order for Bitcoin to work. But if those same complexity theoretic conjectures are true, then there is no black hole information paradox. So, that was it. I'll leave you with a digestible format conclusion. There is a conflict of cosmic proportions in physics. On the one hand, we have general relativity, and on the other hand, we have quantum physics, and they disagree. Except Bitcoin fixes this. Thank you.
What a ride.
What a ride, yeah.
Questions?
I think we needed